Everyone's back, so it's great. So let's talk about the last major big idea. So this is the idea of resonance structures. So sometimes there is more than one way to draw a molecule. So these different drawings are called resonance structures. So the molecule, it's very important to remember that the molecule is not alternating between resonance structures, okay? It's not like going back and forth between two states. It's a mathematical average of the resonance structures, okay? So some resonance structures are more important than others and some are less important, but the overall picture is an average, a weighted average of all of those different pictures. So let's consider benzene. So this is the structure of benzene, which is a carcinogen, because basically benzene is a flat molecule, so it can slip in between the spaces between DNA bases in DNA. So DNA is like a helix with base pairs, alternating base pairs, stacked one on top of each other. So benzene will go in between those base pairs and disrupt the structure. So it causes cancer. So you can see that we can either draw the double bonds like this, or we can draw them like this, right? So these are both resonance structures of benzene. So the actual benzene molecule is an average of these pictures. So to indicate that, so all of these bonds, all the 6 carbon-carbon bonds are the same. And in this picture, the hydrogens are omitted, which is common practice in organic chemistry. So you can see they draw a circle to indicate that all of these bonds are the same. So these aren't double bonds, they aren't single bonds, they're really more like one and a half bonds, if that makes any sense. So how do we determine which resonance structures are important? So we need to follow the octet rule, if it's possible. Sometimes it's not, but you do need to follow, but the octet rule is the most important in this case, except for the exception to the octet rule. So does everyone remember the octet rule, right? So can someone just say what the octet rule is? Just to make sure everyone knows. Right, okay, yeah, 8. So you want 8 valence electrons, okay. The second important idea is to minimize formal charges, okay? And the last important idea is to put more negative formal charges on electronegative elements. So remember that electronegative elements kind of like electrons. So a more negative charge, they don't mind a more negative charge. But we do want to minimize formal charges overall. So, okay. So, for example, so the example I have here is the cyanate ion. So cyanate, C-Y-A-N-A-T-E. So there are 3 major resonance structures for the cyanate ion. So do all of these obey the octet rule? What do you think? Which ones obey the octet rule? Which ones don't? What do you think? Great, so they all follow the octet rule. Okay, so we can eliminate that rule. So now we need to minimize formal charges. So they've very nicely written the formal charges down here. So yeah, so you can confirm for yourself that these formal charges are correct. So this one has this big -2 formal charge. This is, so a +2 or a -2 formal charge is usually not super good. So this is not a very important resonance structure. So this structure is not, does not make a big contribution to the overall picture. So now let's look at this picture. So the formal charges are minimized, right? So a -1 charge or a +1 charge is perfectly fine. So it's not too, 0 is better, but in this case, if that's not possible, since this is, yeah. Oh, and by the way, so the sum of the formal charges, recall, is the sum of the total ion. So you can see -2 and +1 gives you -1, -1, yeah. So this one has a -1 charge on nitrogen, and this one has a -1 charge on oxygen. So remember that oxygen is more electronegative because if you look at the periodic table, it's closer to the upper right. So this is the most important this is the most important resonance structure. This is also somewhat important, and then this one is not super important. So, so what does this tell us? So this tells us that the nitrogen-carbon bond is closer to a triple bond, and the carbon-oxygen bond is closer to a single bond. So triple bonds are stronger than double bonds, which are stronger than single bonds, and triple bonds are shorter than double bonds, which are shorter than single bonds. So we should expect that the carbon-nitrogen bond is short and the carbon-oxygen bond is long. Does anyone have any questions about that example? Okay. So let's look at this example. So this is what's called a ketone. So where R just represents some group, it doesn't really matter. So can someone tell me what you think is the more important resonance structure? The one on the left or the one on the right? Oh, and by the way, the lone pairs are not drawn, but I can draw them if we need. Okay. So can someone tell me which one is more important? Great, so the one on the left is more important because we've minimized the formal charges. See, here we have a plus formal charge and a minus charge. So we minimize that. And also this one violates the octet rule. So you can see that this carbon has 1, 2, 3, 4, 5, 6 electrons. And this one and the oxygen has 1, 2, 3, 4, 5, 6, 7, 8. So the oxygen is fine, but the carbon violates the octet rule. So not good. So yeah, in practice, so this resonance structure is not very important at all. And the carbon-oxygen bond is basically a double bond. Okay. So let's do a tough example. So this is the structure of the nitrate ion. So I want you to draw the resonance structures of the nitrate ion and determine the formal charges. So remember that the whole thing is 1 minus. Yeah. So since we're not sure on how to do this, okay, so first, so this one is hard, right? Okay, so let me think of the best way to do this systematically. So first off, let's give the nitrogen 3 bonds, I guess. So we can do this. Okay. So now what do we have? Okay. So now we have this picture. Because there's a way to explain that. I'm trying to think of the best way to do it. Okay, yeah, let's do this way. So how did I come up with this? Oh, this paper's bleeding. Okay, we get a new sheet of paper. Yeah. Okay, so we start off with this. Is anyone confused? Does everyone understand how I came up with this picture? Does everyone get this? So each oxygen starts off with 6 electrons and each nitrogen starts off with 5, right? Okay. So now let's just form a single bond. Oh, I drew this awfully. So let me do it again. Okay. So does everyone how we got from this to this? Does everyone see how we got from this to this? Okay. So now remember that the nitrate ion is 1 minus. So what does this mean? How many electrons should we add or remove? Okay. So we need to add 1 electron to the molecule because the overall molecule is 1 minus. So it turns out that this oxygen has 1, 2, 3, 4, 5, 6, 7 electrons, right? So if we add 1 more to it, now our octet is complete. However, we still need to complete these the octets of these oxygen atoms, right? So does anyone have a suggestion on how we could complete it? So consider we still have these lone pairs and they're not doing anything. So what should we do with them? What should we do with these 2 electrons? Great, we need to form double bonds. Okay. So this electron, so we'll move this electron onto this oxygen atom. And then this electron will go to form a double bond with this electron. So we end up getting something that looks like this. Okay, does everyone see how we did that? Is any questions? Is anyone confused? Okay. So now we need to determine formal charges. So now we have this, and it's minus. So can someone tell me the formal charges? Okay, so what's the formal charge of? So I'll label these 1, 2, 3, 4. So can someone tell me the charge on atom 1? So the nitrogen atom, what's the formal charge of the nitrogen atom? Okay, so no, it's okay. So let's just walk through this. So we need to split this bond. So we give the nitrogen 1 electron from this bond. and then 1 electron from this bond. And then this is a double bond, so it has 4 electrons in total, so we split that in half and give the nitrogen 2 electrons. So we're left with this, right? And then I'll just draw the rest too. Right, does everyone see how we got that? So now this has 4 electrons, and a neutral nitrogen atom has 5 valence electrons, so this is +1. And then a neutral oxygen atom, so can someone tell me what the charges on the other atoms are? Okay, interesting answers. So how many valence electrons does a neutral oxygen atom have? Right, 6. So here we have 1, 2, 3, 4, 5, 6, 7. So that's an extra negative electron. That's an extra electron, which gives it an extra negative charge. So this is -1, and the same logic is here, and then this is 0. And what you notice is that the total of all of these is -1. So -1 plus +1 plus -1 equals -1, which is the charge on the ion. Like mind blown, right? Okay. So does everyone understand that? Okay. So now let's move on to the second part of the question, the resonance structures. This should be okay. And since it's charged, we can put it in brackets. Minus. Okay. So now, what are the resonance structures of this? So we can draw this double bond between any of the nitrogens and any of the oxygens. So we could draw it like this. And this is equally valid. Oh, and that should be a double side pair. Or we can draw it like this, and I'll draw the movement of electrons. So this lone pair moves to form a double bond, and then this bonding pair moves onto the oxygen atom. So now we have this. So then all of these are equally valid resonance structures, right? Because they all have the same formal charges, they all follow the octet rule, so they're all fine. So they're all equally fine. Okay, so that's why we have this picture like this. So all of them have a single bond, but then the double bond is spread across the entire molecule. So the double bond isn't anywhere at once. It's just mathematically spread over the whole molecule. So this is why it's a partial double bond. So it's actually a 1 1/3 bond. Okay. Yeah. So it's a 1 1/3 bond because the double bond is split over the entire molecule. So it's split between the 3 oxygens. So 1/3 is 1/3. And then plus the single bond. So it's a 1 1/3 bond. So this is a 1 1/3 bond. So I have this interesting picture of the nitrogen cycle. So yeah. So this is something about nitrate. Okay. So what do you guys want to do? So we can either do more problems. We can talk about molecular geometry, or we can talk about molecular orbital theory. So what do you guys want to do? So I guess I should introduce those concepts. So more problems is what it sounds like. So we're just going to look at these molecules. So molecular geometry is all about the shapes of molecules. So how do we decide on shapes of molecules? And I made a handout covering that. Or we can talk about molecular orbital theory, which is not in the AP curriculum, but I thought it would be just something nice to talk about. And you don't have to take notes on it. You can just listen. So, and it's about, so basically all of what I'm talking about, so what I've been talking about for the past hour and a half was formulated a very long time ago. And it has some problems. So for example, you may have seen in the picture of the oxygen molecule we drew earlier, so like this, all of the electrons are paired, right? All of the electrons are in these either bonding pairs or lone pairs. So using this picture, we would predict that oxygen gas should repel magnetic fields for reasons we don't need to go into. However, if you take oxygen gas and turn it into a liquid, it's this blue liquid, and it turns out it attracts a magnet, which doesn't make sense given this model. So we can explain this phenomenon using molecular orbital theory, just to introduce what that is. So what do you guys want to do? So you can either vote for could either vote for VSEPR or MO. Okay, so molecular geometry. We have one vote for molecular geometry. So do we have any other votes? No? Okay. Both topics start with the word molecular, so that can mean either one of them. Okay, so we have 2 votes for molecular geometry and 1 vote for MO theory. So, or we can do problems. Okay. So, so I think geometry wins out. So let's talk about that for a little bit. And this is a lot. So I have a handout here. Okay. So valence shell electron pair repulsion and molecular geometry. So this is what VSEPR stands for, valence shell electron pair repulsion. So molecular geometry is very important because it can decide some of the properties of that substance. So you know, in for example, in a water molecule, water molecules are not straight. So this is not right. They're bent like this. And the oxygen has a partial negative charge, and the hydrogens each have a partial positive charge because of the electronegativity difference we talked. So oxygen is more electronegative, it hogs electrons. The hydrogen is less electronegative, so it has a positive charge. Okay. So, and this gives it what we call a dipole moment. So we have a positively charged end and a negatively charged end, usually represented by this kind of shape. Okay. So because of this, the positively charged end of a water molecule is attracted to the negatively charged end of another water molecule. So, yeah, so water molecules stick together. There's also another phenomenon called hydrogen bonding, which I won't talk about right now. But because of this attraction between water molecules, water has a relatively high boiling point. So water is a very small molecule. They shouldn't really stick together compared to other small molecules like methane or ammonia, which are both gases. Water molecules, water boils at 100 C, which is very high. Okay. So how do we explain this molecular geometry? So basically the idea is that electron pairs will repel each other. So all of the bonds repel each other and the lone pairs all repel each other. So they want to position themselves in a way that minimizes this repulsion. So in VS-EPR theory, double bonds are considered to be the same as triple bonds, okay? And triple bonds and double bonds are the same as single bonds. So we can ignore those. Okay. So let's look at this CO2 molecule. So this carbon atom does not have any lone pairs, right? And the lone pairs on the oxygen are not drawn since they don't impact anything. So these double bonds will repel each other. So we have two things on this carbon atom that are repelling each other. So how do we minimize their repulsion? Well, all we need to do is put them on opposite sides of the carbon atom. So CO2 is linear, it's a line. And by the way, this stuff is on the AP curriculum. So yeah, I think so. I don't know. So we call the total number of lone pairs and bonds. So we count double and triple bonds as a single bond to be the steric number. So all molecules with a steric number of 2 are linear. Okay. So it's the total number of bonds and lone pairs. So here in carbon, on this carbon dioxide molecule, we consider these double bonds to be single bonds. So let's just pretend that these are single bonds. So then we have 1, 2, and then no lone pairs. So we have a steric number of 2. Okay, let's try borane, BH3. So I'll draw the structure of borane. So this is one of our weird exceptions to the octet rule. So you can see the boron only has 6 electrons. So this is a very reactive molecule. Yeah, actually, fun fact. So borane usually exists as diborane. So I'll try to draw it here. So yeah, so diborane is interesting because we have these very strange hydrogen with 2 bonds, right? Very strange. So actually what this is what's called a 3-center 2 electron bond, because this bond has 3 atoms but only 2 electrons. So interesting side note. Okay. So can someone tell me what the steric number of borane is? Looking at the drawing. So what's its steric number? Right, so 3. Exactly. So borane has a steric number of 3 because it has 3 bonds and no lone pairs. So this means that to minimize repulsion, we get this trigonal planar structure. So can someone tell me what the hydrogen boron hydrogen angle is? Can someone tell me what this angle is? Yeah, 120. Okay, great. So everyone here knows math. Great. Okay. So this is methane, CH4. So as you can see, we have 4 bonds, 1, 2, 3, 4. So we have a steric number of 4. So this structure is called the tetrahedron. And it turns out this angle is hard to figure out. You have to do some tough math. So I'll just tell you, it's about 109.5 degrees. So this is a number you should know. Okay, so I would write it down in your notes or something. So this angle is 109.5. Okay. Okay, so PF5, this is tricky. So can someone tell me what the problem with this molecule is? So count how many electrons does the phosphorus have? Okay, so it has 5 bonding pairs, but remember that each bond has 2 electrons. So it's 10, right? Okay, so you might have, that's more than the octet rule would suggest. So it turns out that elements that are on row number 3 of the periodic table, so period 3 and below, can have expanded octets, or what's called an expanded valence. And the traditional explanation for this is that you can have an involvement of the d orbitals. So and however, computational studies suggest that this is not true. And if you want, I can show you, I have a nice paper kind of explaining this expanded octet. But just don't worry about it for now. Just note that elements on row number 3 of the periodic table. So let me show you. So from here and below, so here and below, you can have an expand. You can have more than the octet rule. These elements never have expanded octets, really. Almost never. So, yeah. Because for these elements, the d orbitals are very, very high in energy. So to utilize them is not okay. So that's the traditional explanation. And another explanation is that these elements are kind of small, so you can't fit so many things around the small element. So that's another explanation. Okay, so with that out of the way, so this is what we call a trigonal bipyramidal structure. So you can see we have a triangle, and then you can form a pyramid. Okay, and then there's 2 sides, so it's a trigonal bipyramidal. And what's interesting about this structure is that we have different positions. So these 3 positions, the 3 positions in the triangle, are called the equatorial positions, and these 2 positions are called the axial positions, and they're not the same. So the axial positions, so this bond, which I'm circling with my mouse, is actually weaker than this bond, which because of reasons which have to do with molecular orbital theory. So this bond is actually longer than this bond. But at any reasonable, at a high temperature, so like at like room temperature and stuff, all of these positions are rapidly interconverting. So this molecule is constantly molecules are constantly jiggling around. So these positions are constantly being switched. So you don't observe this in real life. But if you were to cool it down to like, I don't know, like -100 Celsius, or if you were to take a crystal of it, you would see that there's a difference between these 2. And then SF6, which also exhibits your expanded valence, is just an octahedron. So SF6. And all of these are the same, basically. Yeah. Okay. So do we have any questions on what I just covered? So I didn't really make practice problems, but I can do one example. So here we have the sulfate ion. And I didn't draw the lone pairs in, but it's fine. So the sulfur doesn't have any lone pairs. So can someone tell me what geometry this should have? So tell me the steric number and the geometry. Oh, is there a way to tell which bond will be longer, or could it be any of them? So double bonds are shorter than double bonds are shorter than single bonds, and triple bonds are shorter than double bonds. And for the trigonal bipyramidal structure, the axial bonds are just longer because they have more repulsion and they're weaker. But yeah, hard to say. If you have heavier elements, so like further down the periodic table, the bond lengths will be longer too because the atoms are just bigger. So I hope that answers your question. So can someone tell me the steric number? Yeah, great. So 4. And then what's the geometry? So I'll go back to the picture here. So which one of these is it? So steric number 4 is a tetrahedral structure. So which one of these is tetrahedral? So upper right, upper left. Great, so it's the upper right structure. So this is, yep, so that's the structure of the sulfate ion. And because of resonance structures, all of these bonds are equivalent in the sulfate ion. They're all the same. So, if you want, so I also want, so for homework, I want you to read the rest of this handout because it's too many pictures to cover in the lecture itself. Okay, so now I think would be a good time, since we only have 5 minutes left, to just do these problems. So I want to do the first 4 because this is interesting. So the atoms are connected in the order I've written them. So this is N bonded to C, and the C is bonded to O. So these are all linear. These are all kind of in a line. So I want, can you draw Lewis structures for all of these and assign the formal charges? You until 9 o'clock, and then I'll go over the answer. To run out of time, so let's just go over this problem, and I will post the homework sometime tonight. Okay. So let's start with NCO. Okay. Oh, let me clear everything. Okay, so we have these 3 different possibilities to arrange our atoms. Let's just go through them one by one. So first of all of these are minus charged, so we know that. Let's just start by drawing our atoms in. Okay, so 1, 2. So we have a minus charge. So we need to add 1 electron. So for now, let's just put it on oxygen. So let's draw our, okay, so our oxygen has a -1 formal charge. So we can draw a single bond between the carbon and oxygen, and a triple bond here. And these have 0 formal charges. Right? Oh, Oh, did I get this wrong? Okay, wait. So that should be O and C. Okay. Minus. So this is the cyanate ion. And as you can see, we have a very small formal charge, and it's on an electronegative element. So this is a fairly stable ion. Okay. So now let's move on to this one. So we still have a minus charge. This one's a bit more difficult. So what we can do is, why don't we just put in a triple bond here, single bond here, and a lone pair here. Here. Right. Okay. So we have this. How do you derive these things? I would just mess around until you get them, until you have a solution that fulfills the octet rule. And just make sure to add the right amount of electrons, okay? So you can always confirm your answers by summing up the formal charges and yeah, and making sure that adds up to the total charge of the molecule. So, I mean, I've had a lot of practice with this kind of stuff, especially with organic chemistry. Like you have to draw these huge structures. So I have a lot of practice with this stuff. So I think this comes with practice a lot. But if I find a more intuitive way of getting these structures, I'll write up a handout and send it to you guys. Okay? So can someone tell me what the formal charges here are for this structure? Perfect. So now we have a lot of formal charges. So this isomer, so this arrangement of atoms is less stable, but they're only 1 minus, so it's not too bad. Could be worse. So this ion can be isolated. It is somewhat stable, and one common example is this. So this is mercury 2-fulminate. So let me write it down. And this is a high explosive, which is used to detonate other explosives. Okay. So now I have trouble with this one. It's very hard to draw a reasonable resonance structure for this one. So we can give it a go. So let's try to draw. So let's try this first. So this is 2 minus, and then. So this does follow the octet rule, but it's kind of ridiculous. And okay, so that's not right. So let's try again. Maybe this works. Okay, and then we can do that. So and then this moves to here. So this is the best one I can come up with. And so can someone tell me what the formal charges here are? So -2, +2, and -1. Okay, so that's right. So these formal charges are huge. So that's one thing. Additionally, what do you notice? We have this +2 oxygen. That's ridiculous. So oxygen is very electronegative, and we're giving it a 2+ charge, which is insane. So this ion is very unstable, and it doesn't exist. So it's never been isolated. So maybe if you can isolate it, you'll get a Nobel Prize. So yeah, so this is just shows how the predictive property of formal charges. So we go from low formal charges, stable, to more formal charges, somewhat less stable, to ton of formal charges, and it doesn't exist. Okay, and I think that's the end of the lesson. So